Hello everyone. Now I am starting my lecture number 7. In our early lectures, we studied about two functions, that is sigma function and tau function. So here we'll start about Möbius function. So earlier we studied about tau function and sigma function. So what was tau function? Tau function was the number of divisors, positive divisors, and sigma function was the sum of the positive divisors of an integer. Now we'll study about what is Möbius function. So for a positive integer n, say n is any positive integer, then the Möbius arithmetic function is defined as. The definition of Möbius function is quite different from tau function and sigma function. So here we denoted Möbius function as the sign mu of n, where n is an integer. So here we have three cases. The Möbius functions range are always in three values. One is 1 as our sigma and tau. The value of sigma of 1 and tau of 1 and mu of 1 are always equal for n equals to 1. That means if n equals to 1. Another one is the value of mu of n is 0 if the n is not a square free integer. That means if n is not a square free integer, that means there exists a p square which divides n for some prime p. And another one is minus 1 raised to the power r if n is a product of r distinct primes. So if n equals to 1, then the value of mu of n are always equals to 1, and the value of mu is always equals to 0 if n square divides n, p square divides n. That means in statement we can say that if n is not a square free integer, then the value of mu of n is always equal to 0. And the third case is the value of mu of n is always equal to minus 1 raised to the power r if n is a product of r distinct primes. That means if n equals to p1, p2, p3 and so on to pr. So n is a product of r distinct primes. That means and another thing, that for any pi not equals to pj when it is a square free integer. So this will happen for n is a square free, and this will happen for n is not a square free integer. Or in different, we can say this, that there exists a p square in the divisor list of that integer n. So we'll take as earlier also in mu and sigma we have some remarks. So now in Möbius function also we will have some remark, that is if n is a square free integer, that means here it says that n is a square free integer, then as we know n can be expressed as a product of distinct primes. That means the mu of n equals to 1 or minus 1. The value of mu of n depends upon two values, that is 1 or minus 1. So according to the prime, a number of primes is even or odd respectively. For an example, if we take an example that mu of 35, so if we broke the prime factorization of 35, that is 5 cross 7. So here therefore that we can say that the 35 is a square free integer. That means we have two distinct primes. Here the value of r is 2. Here 5 and 7 are two distinct primes. That means the value of mu of 35 will be minus 1 raised to the power r. Here the value of r equals to 2. That means minus 1 raised to the power 2. That means the value will be 1. So our second remark will be the range of mu is always from -1 to 1 with 0. That means we also know that by our definition of Möbius function, that the value of mu always lies between value of mu always can be three numbers, that is -1, 0 and 1. -1 in the case for any square, if n is the factors are square free integers and for distinct primes, and 0 if there is exist a perfect square number in the divisors in the divisor of the number n, and always 1 for the mu of 1 is always equals to 1. So now we broke down various mu functions, that mu of 2 are always equals to -1, mu of 3 is equals to -1, because 2 is depends upon two distinct primes 1 and 2, the two distinct one distinct primes, that is -2 is equals to, you can write it in the form of 2, that is one distinct primes, that means -1 raised to the power 1, that means the value of mu 2 is equals to 1, mu of 3 is equals to -2, and mu of, because in case of mu 3 the factorization is only divisor is only 3, mu of 4 is equals to 0, because in 4 prime factorization we have 2 square, that is a square, that is a perfect square or a squared number, because because there exists a squared number in the prime factorization of the n, here n is 4, then it will be 0. The mu of 5 equals to -1, mu of 6 equal to 1, and so on, mu of 13 equals to 1. So in this case, in this list, we can easily see a simple similarity, that mu of 13 equals to -1, mu of 11 equals to -1, mu of 7 equals to -1, mu of 5 equals to -1, 3, and mu of 2 equals to -1. So in these cases we can easily say our fourth remark, that is mu of p is always equals to -1 for any prime number. The mu of p is always equals to -1 for any prime p. Say mu of 1729 is always equals to -1, because 1729 itself a prime number, that means the value of it will be -1. So if we move towards our next theorem, here it is the function mu is a multiplicative function. Here it is given that the function of mu is a multiplicative function. So if we take that let m comma n belongs to natural number, for to prove any multiplicative function we always take two integers m and n, which is belongs to natural numbers, and another thing, the GCD of m n is always equals to 1. So since we have to prove that mu is a multiplicative function, so that we can we have a claim, that is mu of mn, we can write it in the form of mu of n, product of mu of n and mu of n. It is our claim. So if we take by prove it by cases, so by case 1, as we prove in our first or second lecture, there was a question that says that prove that tau is a multiplicative function or sigma is a multiplicative function. There we start our proof by claiming as per our first case, we take that m equals to 1 and n equals to 1, and for mn and both equals to 1, we took 3 cases. So all of these 3 cases, here we are taking this as case number 1. So if m or n or both m comma n is 1, then we are through. Then we can easily prove by our early theorems, by we need not to show. So in our case 2, we have again that we are taking, we already proved that for m equals to n equals to n, for m and n both equals to 1. Now you have to show that if the value of m and n are greater than 1. So if m greater than 1 and n also greater than 1, and we are taking that p square divides m or p square divides n, then we can say p square divides mn. Wait, I will say. So if we say, suppose taking another ink, if we say that if we say that 4 divides 8, or 4 is a divisor of 8, and 4 divides 12, which is also true, then we can easily say that 4 divides the product of 8 cross 12. So this is true, and so here I wrote that either p square equals p square divides m or p square divides n, then p square divides m, and here I write it either. So I am giving an example for the portion of either, that if 4 divides 8, 8 divides 4, but or 8 is 4 is a divisor of 8, and 4 does not divise 15, then also we can say that 4 divides the product of 8 cross 15, which is true. So similar thing I took here, that if either p square divides m or p square divides n, then p square divides obviously divides mn, which is true. So here, from here we can easily wrote that mu of mn equals to 0 equals to mu of m dot mu of n. So we are now moving towards our case number 3. So in our case number 3, we are suppose let m, again m and n both greater than 1, and mn are square free integer, and m, and we are specifying our theorems more. Let for every numbers, for every m and n integers, that means let m and n both are greater than 1, and m and n are square free integer. That means we can write m as the product of p1, p2 and pr, the prime factorization of m, and so n equals to q1 dot q2 and so on qr. So if we find the product of both of these m and n, we will have m dot n equals to p1 p2 dot pr, and another one will be q1 q2 dot qs. That means we can write where for no pi equals to any qj, because we are taking that m and n are square free. So here we can write mu of mn. So here we wrote that mu of mn, so we can write that p1 p2 dot pr, here it is a product of distinct primes, so it satisfies our third property, that for the product of distinct primes the mu value are always equals to -1 raised to the power r, and this will -1 raised to the power s. which is nothing but our mu of m, and which is nothing but our mu of s, sorry, mu of n. That means we can say that thus mu is a multiplicative function for all m comma n belongs to positive integers or natural numbers. So we already proved that tau, sigma and mu, all of three are multiplicative. That means tau of mn is also, we showed it is a multiplicative, that it satisfies the tau of m dot tau of n, sigma of mn also satisfied that sigma of m dot sigma of n, and for mu, that is mu of mn, we now showed that mu of m dot mu of n. This is our results of this is not actually the results from our theorem, this is the results of our lectures notes. So we move forward our next question. Here it is saying that for any integer n greater than equals to 1, prove that, we have to prove that summation d divided n mu of d equals to 1 or 0. 1 is always if n equals to 1, and 0 when n greater than 1, where d runs through the positive divisors of n. So we are starting, before starting our proof, let us check with an example. Suppose we are taking, suppose here I am taking that mu summation d divides 10 mu of d. If we broke it down, then we will have mu of 1 plus mu of 2 plus mu of 5 plus mu of 10. Here 1, 2, 5 and 10 are the 4 divisors of 10. So mu of 1 is always equals to 1 we have, and mu of 2 is always equal to -1, mu of 5 is always equals to -1, and the last one, the mu of 10, which is the product of distinct primes, which is always equals to -1 raised to the power 4, which is +1. That means we have 1, -1, -1, +1. If we cancel out, we have the answer 0. So it satisfies our property that for any n greater than 1, the value here we take that n equals to 10. Here we are taking that n equals to 10. For any n greater than 10, it satisfies our property, and we already know by our definition for n equals to 1, the mu value of 1 is always, mu of n is always equals to 1 for n equals to, if n equals to 1. So let me start our theorem, saying for we'll start now by, let me take an ink. Here for n equals to 1, our summation d divides n mu d equals to summation d divides 1. There will be only mu d equals to mu of 1, which is always equals to 1 by definition. So in next case, let us define. What will you define? That capital F of n equals to summation mu of d for some d divides n. So by our known result of if f is a multiplicative, f of n is always equals to f of d. If we already proved that capital F of n equals to summation small f of d, d divides n. Since, so we can say that since if mu as mu is a multiplicative function, then f is also a multiplicative function. Since mu is a multiplicative function, then we can say that f is a multiplicative function. Why? Because mu is a multiplicative function. So now we are taking for n greater than equals to 1, our second case, that n has a prime factorization of, we can write that n as the prime factorization of p1 alpha 1, p2 alpha 2, and to pr alpha r. So the value of capital F of n will be the f of p1 alpha 1 dot p2 alpha 2 and so on pr alpha r. So since f is a capital F is a multiplicative function, then we can write this line as the f of p1 alpha 1, f of p2 alpha 2, f of pr alpha. So we can write this f of p1 alpha 1 dot f of p2 alpha 2 and so on f of pr alpha r. So now so here p1 alpha 1, p2 alpha 2, pr alpha r, since all are the product of distinct primes, so we are now taking as, or alpha value is for any alpha 1 alpha 2 alpha r, we are taking for f of p of alpha. That means it will summation d divides p of alpha mu d. So it is our it is as our, now we can define it as our last lecture of tau and sigma function, which is lecture number 6 and lecture number 5. That means we can write that mu of 1 plus mu of p plus mu of p square plus so on dot mu of p raised to the power alpha. So in our in our last class that we defined that we wrote that sigma of p square at 1 plus p square and p raised to the power alpha as 1 plus p square plus p cube dot p raised to the power alpha. So in this case we will not break it down that in that manner. We will find it that we all know that the value of mu of 1 is always equals to 1, and mu of any prime number is equals to -1. So for next number that means in p square, that is a repetition of prime number, there is a repetition of prime number exist. That means the value, if repetition exists, then it is not a square free number will be there. In case of mu of p square, there must not be a square free integers in these divisors. That means the value of this will always equals to 0, and so on. The mu of p cube, there also exist mu of p square, that also used, and so on. The value of mu of p raised to the power alpha is must be always equals to 0. So the value of this 1 is 1 minus 1, that means the value of f raised to p raised to the power alpha is equals to 0. Therefore we can write that the value of f of n equals to sigma of mu d for d divides n. So it showed that for any n greater than 1, the value of uh, if n greater than 1, the value of mu d is always equals to 0, where d runs through the positive divisors of n. So if we move forward our next example, here it is that for each positive integer n, we have to show that mu of n is can be written in the product of consecutive integers, that is in the mu function of consecutive integers, that is mu of n plus 1, mu of n plus 2, mu of n plus 3. So if we write it in the form that 1 2 3 4 5 6 7 8 9 10 11 12, so here I wrote 4 group of numbers. So what is the similarity of these numbers? In first case, that if we take the consecutive integers, the GCD of the consecutive integers is always equals to 1. And in another case, that we can say that if we take 4 consecutive integers or from any positive any numbers, then it must be divided by n 4 factorial, or in case of, we can say that if we take that n plus 1, n plus 2, n plus 3. So we can say that if n plus 1, n plus 2, n plus 3 are the consecutive integers, where n is an integer and this is a consecutive numbers list, then it must divide by a number. Actually here we have 1 2 3 4 numbers, then it must be divided by 4 factorial. And if we take another number, that n plus 4, then it will it says that it will it will divide by 5 factorial. That means we have a theorem in our basics of number, that if we take any 3 4 5 6 7 8 n number of integers, and if we found the product of n number of positive n number of integers, then it must be divided by the number n factorial itself. So it is an example. So if we move towards our proof, so we can say that since mu of since n plus 1, n plus 2, or n plus 3, as what is this, these are consecutive integers, we know that for product of 4 consecutive integers are also divisible by 4 factorial. Here we have 4 consecutive integers. That means it will must be divided by 4 factorial. There, that means 2 square, that means 2 square equals to 4 always divides n into n plus 1 into n plus 2 into n plus 3. As we know that mu is a multiplicative function, and as we know that the GCD of n plus 1, n plus 2, and n plus 3 is equals to 1. That means mu of n dot mu of n plus 1 dot mu of n plus 2, as we know that mu is a multiplicative function, that n mu of n plus 3 is always equals to nothing but 0, because there exist because mu k is 0, because there exists a p square divides our k. So let us move to our next example, which is say that for any integer n greater than equals to 3, we have to show that there is a summation equals to 1 to n mu of k factorial is equals to 1. So we are concluding this as our we have some technical errors. That means for any, if n greater than equals to 4, then n factorial will contain 4 as a factor, as we have that n greater than equals to 3 and it runs from k equals to 1 to n. In case of n greater than equals to 4, that means there we have a 4 as a factor, then since mu is a multiplicative function in nature, so n greater than equals to 4, that means mu of n factorial will be mu of n dot mu of n minus 1 dot mu of 4 mu of 3 mu of 2 dot mu of 1, which is equals to must be equals to 0, because there exists mu of 4. We can say that the mu of 4 is a squared number, perfect square. 4 is a square free number because in the divisor, in the prime factorization of 4, there exists a m square, that is 2 square, that the value of the value of mu of 4 must be equals to 0. Then if we can find out that there is a 0 in the product of mu of n minus 1 dot so on and to mu of 1, so we can say that the number will be 0. Therefore we only to consider the case for n equals to 3. So for k equals to 1 to 3, not n, we have mu of k factorial, that means mu of 1 plus mu of 2 factorial plus mu of 3 factorial, that means mu of 1 plus mu of 2 plus mu of 6, that means the value of mu 1 is equals to 1 and mu of 6 is equals to, it is equals to minus 1, because in case of 2 is a prime number, the mu value of prime is always equals to minus 1, and in case of 6 we have 2 3 the 6, that means we have factors 2 and 3 as a prime factor of 6, that means minus 1 raised to the power 2, the minus 1 raised to the power 2 is always equals to 1, that means the value will be 1. So here we studied about mu function, what is mu function definition and some examples, and in our next lecture we will study about if some Möbius inversion formula. So till now we studied about the Möbius function, and Möbius function is multiplicative or not, and some important examples and theorems. So let me conclude here. So in our next lecture we will study about that Möbius inversion formula. Thank you.